Okay, so looking at page 115 in our student journal, the first thing we're going to start with are even and odd functions. So it says a function f is an even function when f of negative x equals f of x for all x in its domain. Also, the graph of an even function is symmetric about the y-axis. So first of all, let's look at the way an even function would appear. This is an even function. This is the y-axis. Notice how it is symmetric when about that y-axis. In other words, the point xy is here, the point negative xy is here, so therefore it is symmetric about that y-axis. We could fold over that y-axis and the one side would go right on top of the other. Let me show you the example of an equation that would be symmetric with respect to the y-axis and would also be an even function. So look at this function. Let's say we have f of x equals 3x to the fourth minus 4x squared. So I'm already telling you this is an even function. But if I asked you to prove that it's an even function, you would have to do this. We would have to plug in negative x anywhere we see an x. So to find this f of negative x, wherever I see an x, I plug in a negative. And then we want to evaluate that. So what's a negative to the fourth power going to be? Positive times 3. So this is positive 3x to the fourth. And then a negative x squared would be what? Positive x squared times a negative would be minus 4x squared. So when we plugged in the negative x, did we get exactly the same equation as what we started with? Yes. So that's what makes this an even function, because that happened. So an odd function, though, it says a function f is an odd function when f of negative x, in other words, replacing x with a negative, results in negative f of x. So up here, it means no signs change from the original to f of negative x. But this is going to mean that all of them change. So when we have an even function, we plug in negative x, we get the exact same function back. But when we plug in a negative x and it's an odd function, we get the opposite of the original function. All of the signs change. Also, the graph of an odd function is symmetric about the origin. So see, this is symmetry with respect to the origin. A point xy would be the same as the point negative x, negative y. A point here, like let's say this point right here, this might be the point, say, 3, 1. So we would also have the point over here of negative 3, negative 1. That's what we mean by an odd function. So let's look at an odd function. So what if we have g of x equals 2x to the third minus 5x? We're going to show that this is an odd function. So here's what we do. We plug in a negative x. Everywhere we see an x, we plug in a negative x. And when we do that, a negative x to the third is a negative. Times 2 would be a negative 2x to the third. A negative x times negative 5 would give us a positive 5x. So look at our original function here, and now look at the result. What happened to the signs of both of these? They both what? They changed from what they were originally, weren't they? And that's what's always going to happen if we have an odd function. Now, there should be something else that you notice when we have an even function and when we have an odd function. Does anyone see what it would be? Yeah, Michelle? Right. If all of our exponents are even, it's going to be an even function. If all of our exponents are odd, it's going to be an odd function. Okay? So let's look at the case where it's neither even nor odd. H of x equals, let's say we've got negative 4 x to the third plus 6. A lot of times people would say, oh, this has to be odd, right? Because I have an odd exponent there. But what's the exponent here if there isn't one? 0. 0 is considered an even number. So therefore, this is going to be neither. Let me prove it to you another way. If I plug in a negative x, I would have negative 4, negative x to the third. There's nothing to plug in for there. Negative x to the third is a negative times 4 would be a positive 4x to the third, and this would just stay plus 6. So to have an even function, none of the signs change from here to here. To have an odd function, the entire function must change. All the signs must change, and they do not. So this is going to be neither. All right. So what's the symmetry on this one? Origin or y-axis? Y-axis. And in fact, let's just check that out. Let's see what that looks like, that function. Just going to clear everything. We'll see if Maya's correct. She said this one should be symmetric with respect to the y-axis. Here's the way it looks. It is symmetric with respect to the y-axis, isn't it? Okay? So this gives us an idea of how to check our graphs. Like if we know something should be an even function, then we should see that symmetry with respect to the y-axis. If it's odd, the symmetry with respect to the origin. Okay, we are going to graph one function on the back. We're going to do number 2, but we have to do a lot with it. It says in exercises 1 through 6, first of all, we have to graph. Then we have to find the x-intercepts. We have to find the points where we have local maxes and local mins. That's the third thing. We have to determine the intervals on which the function is increasing or decreasing, so that's the fourth thing. And we have to determine whether the function is even, odd, or neither. We can probably do that right now. I want you to think about that. Look at the exponents. Tell me whether this is even, odd, or neither. Neither, correct. So this is neither even nor odd. Okay, and this is going to take us a lot of space. We're going to use our graphing calculator to help us with this because it's a very involved problem. So let's type it in. So once we have it typed in, we should do a zoom 6. Take a look at the graph. And it's pretty hard to see what's going on with this window. So I'm going to definitely want to see down lower. One thing I can see, though, is that it almost looks like there's 2 x-intercepts in there. I'm going to have to be aware of that. There are 2 of them, because see how it goes up higher there? So we can see that there are. In fact, if I really want to see that for sure, I might want to even zoom in first. Watch how I'm going to get closer in just to see that a little better. Just looking at that middle part. Do you see how there are 2 x-intercepts there? Okay, so we're going to have to find 1, 2, 3, 4 x-intercepts. Now, here's the thing, though. If we want to see the bottom of this graph, I have to make it go down much further. So I'm going to make this graph go down to like negative 60. I don't know. We'll see what happens. I want to see the bottom. Nope, I still can't see the bottom. Make it go down a little bit further. Go to your window. Maybe negative 120. Hopefully that'll do it. Oh, darn. So we got to make it go even a little further still. There we go. And see how now it looks like we don't have two x-intercepts there? It almost looks like a bounce now, doesn't it? That's why we have to be a little bit smarter than the calculator, because we can't just go with the fact, well, hey, that looks like a bounce. It really wasn't. We looked at it earlier. So we have to find 4 x-intercepts. What's the y value when we have an x-intercept? 0, right? So we're going to go to y equals, and we're going to put in y equals 0. Because if I go to my table, I only see one x-intercept right there. Okay, so we can go ahead and list that. So over here, I'm going to put my x-intercepts. I do know that 0 is one of them. But we have some others. Look here, guys. See how this is going from negative 104 to 150? It has to touch 0 in between there. So there has to be an x-intercept in between there. Also here, look at those y's. It goes from a negative to a positive. It has to cross 0. There has to be a 0 in between there. So let's find these x-intercepts. Here's what we do. We're going to go to second trace. We want to find the point of intersection. And I want to go, I'm going to go way down here and I'm going to find them from left to right. So I'm going to go way down to that first one, and I have to be close to it for it to know which one to find. Then I just hit enter to tell that's my first curve. Yes, that is my second curve. So I hit enter, and I hit enter one more time. And there's my point of intersection, negative 4.56. Maybe we should be writing these as ordered pairs. Let's do that. So let's write our first x-intercept is 0, 0. Our next one, negative 4.560. Now remember, there were actually 2 right in here. We already have the 0, 0 one, but I have to get close to this next one. That's probably close enough. Enter, enter, enter. There's that one that's hard to see, negative 4.4, or not negative 0.44 rather. There's another one, and then we got to find this last one down here. So let's go to second, trace, intersect, find that one too. Got to get down close enough, enter, enter, enter. What happens, guys, is we have to get beyond the turning point. Otherwise, it's not going to find the one we wanted to find. And so here's our last x-intercept. So now we're going to plot those on here. So 0, 0, negative 4.56, negative 0.44, 2.5. Okay, now to be able to graph this well, okay, so we're starting the graph, we've done the x-intercepts. Now we have to find the points of the local max and local min. So right here, this is the local min. We have to find it. Here's how we find it. Second, trace. Which one do you think we'd use? Minimum, right? Since we're trying to find a minimum, so number 3. So we now have to go to the left of that minimum. I'm going to go ahead and find this one since that's what I'm closest to. You can find this one if you're closer to that one. Here's how I do it. I have to be on the left side of it, and then I hit enter. Oops. Hold on. Let me do that again. It's kind of messed up. Second graph. So I have to do second trace. I want a minimum. I have to go to the left side of it. That's good enough. I hit enter. I have to go to the right side of it, arrow over and hit enter. And then one more time, and there it is. So I'm going to jot that down, that I have a minimum, bless you. I have a local min at 1.68, comma, negative 36.4. Just round that to the nearest tenth there. Okay, so now I'm going to plot that. Well, I'm going to wait because this one may be really low. Okay, now we've got a maximum. Do you guys understand why we have a maximum right there? Okay, so we got to find that. So second trace, find that maximum, go to number 4. Got to go to the left side of it. That's far enough. Enter, go to the right side of it. enter, enter one more time, and there we go, negative 0.22. And then the y value was 1.13. Okay, so jot that down. So that's a max, though. That's a local max. Alright, so now I have to find one more thing, guys, just this local min. So stick with me here. Second trace, go to that minimum, number 3, arrow over until you get to the left side of it. Another thing you can do is you can jump. You can actually tell it what to make the left bound. Do you remember what two numbers it was in between? It was in between what, -5 and -4, was it? So I can tell it my left bound is -5. And I can tell it my right bound is -4. But I have to be sure about that, otherwise I'm going to get an error. And then I have to push enter one more time. Ooh, never mind, that didn't work. Okay, let's do it the other way. Must not have been in between those two. So there's my left bound. Oh, it was in between negative. Oh, it was in between -4 and -3. Do you see how that didn't work? If I would have done between -4 and -3, it would have been fine. So now I have another local min, -3.34, comma, -138.3. All right, so I got to plot these points now. About 1.5 and -30. Let's do this one first, though. I want this to go down by 50. So that's -50, 100, 150. Go down 50, about right there. There's a minimum. I have a maximum at -0.22 right there, just a little bit higher. It's really hard to plot that one. Then we have a minimum at 1.5 and down about 30. That's going to be right about there. And then we know that end behavior was like this. Okay? So there's a pretty good look at what the graph is. And so the last thing we have to do is write the intervals of increase and decrease. So this is going to be decreasing first. It's decreasing from -infinity until I get to this point. That point was -3.34. Then it's increasing. It's increasing from that -3.34 until I get to that point, until I get to that maximum of -0.22. Union, then it starts decreasing. It's decreasing from -0.22 over to this one, which is that one, 1.68. It makes it a little bit easier if you just put these on your actual graph. And then it's going to be increasing again from, what is that, 1.68, yep, to infinity. All right? Does that make sense to everybody? You can do that? All right, good job, guys. So we're going to stop there.